started. We have a lot to cover today, so I'm going to try to pace myself, but please do stop me as always if you have questions. So I'm trying to cover the whole topic or finish the topic today of discriminant analysis, which is a fundamental topic that we needed to cover. So remember, we're talking about discriminant analysis, and we've discussed a variety of methods to solve the problem, and they are all basically, or can they all be summarized as the maximization of this criterion VMWV over V transpose MUV, and our goal is to maximize or to find the V, right, the vector V that maximizes this, where these two matrices here are symmetric and positive semi-definite. Let's say positive definite. If they are not positive definite, we can always project it to the PCA space and make them positive definite. And therefore, they define a metric, right? And that metric basically is what we are going to use to get our results. So we have seen several metrics that I can use for MW and MU. So for example, for MW, I could use the between class scatter matrix, and for MU, I could use the within class scatter matrix, or maybe the covariance matrix, right? And I've posted papers for you in Carmen that specifies other metrics that one could use. Okay. Now, what is important, extremely important for you to get from this is that when you have a specific problem, you want to tailor the metric to that specific problem that you're trying to solve, right? And you want that metric to be base optimal under some reasonable conditions that apply to your problem, right? So that's why this is so useful. It allows you to define different metrics for your problem. Now, remember that we have said that when you apply this algorithm with SB and SW, you get base optimality, right? This result is base optimal. Under the constraints, say if or when the C classes or the C classes are defined by homoscedastic normal distributions, okay? And what we mean by base optimal, we should add here another caveat in the C-1 dimensional space, right? Or subspace, given by this equation, right? Where now V is a matrix whose columns are the eigenvectors or the basis vectors that define that subspace, correct? All right. Now, so we already discussed the problem that this is not as good as our first algorithm derived by Fisher, that for the two-class problem, you can go down to one dimension. Obviously, that particular case, it's defined in here, because if I only have two classes, then this is 2 minus 1, 1. Okay, right. But when C is larger than 2, then this is larger than 1, right? And our algorithm is not guaranteed to find the one-dimensional space where the base error is minimum, meaning that there is no other one-dimensional space you could ever come up with that has a smaller base error once you project all the distributions or all your data in that space. And to show you this, I'll give you a couple of examples. So in our first example, we're going to have 3 classes given by these 3 Gaussian distributions. And now note that the way I'm going to draw them, they are all the 3 classes, or actually, why don't I use different color? That way it'll be even clearer. The way I'm going to draw this is that they correspond to 3 underlying, of course unknown, but 3 underlying homoscedastic normal distributions. Okay, so each color here is going to represent a class. Okay, so let's say that this is class 3. The blue one here is going to be class 2. And this is going to be class 3. Now, obviously, that's not the only way in which 3 classes can be given in a 2-dimensional subspace, right? So, for example, I could have them distributed like this. This one here, this one here. Again, you have better drawings in these slides. I'm trying to draw them as closely as possible to each other. This ellipsoid that represents the covariance matrix of the class. But just note that they are homoscedastic Gaussians. Right? So again, this would be class, whoops. This would be, I have class 3 twice. This class 1, class 2, class 3. And then same here, right? 1, 2, and 3. All right. Now, if I apply, if I compute SB and let's do sigma x. How about if I do sigma x? Okay. So if I compute sigma x, right? So for mu here, I'm going to use sigma x. Okay. And sigma x here is going to look something like this, right? That's sigma x. And here is going to look something like this, right? Correct? Yep. So far, so good. Now, what is SB going to look like in each of these cases? Let's see. SB here, remember SB is going to compute the covariance matrix of the class means, right? So if I have these 3 class means, the covariance matrix of these 3 points is going to be this thing here, right? Right? Approximately. And here, it's going to be pretty much the same thing, right? So you can see that SB here is pretty much the same as this SB. Sigma x is pretty much the same sigma x, right? In the slides that I gave you, they are exactly identical, right? Because I've done this in MATLAB, and I can guarantee that they are actually the same. Now, let's apply this algorithm. Remember, this algorithm is called linear discriminant analysis. Let's apply this algorithm to these 2 classes. And let's just look for the first eigenvector, right? The one that maximizes this metric here. The metric is defined by mu inverse times mw, right? Now, if we do that, let's see. I want to maximize mw, right? Which is SB. So I want to maximize SB, which is the vector or the subspace that would maximize SB, such that if I project that metric SB onto it, SB would be maximized. Anyone? What's that? what would be the way to maximize SB, right? So I have here, I'm trying to maximize, I need to find the V vector that maximizes SB, V transpose S, excuse me, I'm using sigma X, V, right? So for SB, let's forget about this denominator for now. If I want to maximize SB, what would be the V vector?
Leading eigenvector.
Mm-hmm.
Leading eigenvector.
Which one would be here in this space? New one? Where is it again? Yep, okay. The horizontal line, the x coordinate, let's call it. So it would be this one here, right? This subspace defined by this basis vector V, right? That would define this dimension. And if I project now this metric SB onto that single dimension, right? That variance that I get, it's the maximum I can ever get, right? If I rotate this space, this vector, right, for any other vector, I'm going to get another one-dimensional space for which when I project SB onto it, the variance is smaller, right? Clearly. The same applies here, right? For SB, I would like to get this one. Now, what happens for sigma x? Sigma x, I want to minimize it, right? Because this is in the denominator, right? So I want to minimize this metric. What is the dimension that minimizes sigma x? What's that? The orthogonal to the previous one, right? So now I want to select this subspace, right? That's given to me by this other V. So let me call this V the one that maximizes SB, and this one the one that maximizes sigma x, okay? Now, what's the problem with this? Anyone can tell me what the problem with this is? Let's start with this case. What's the problem with this? So remember, I want to maximize this ratio, right? But what's happening? This metric wants to maximize, or wants to select this V vector. This other metric wants to select another vector that's orthogonal to my first one. It couldn't be worse, right? I mean, there's no compromise between the two. They're orthogonal to one another, right? So what is LDA going to do? I mean, it has to make a decision. Is it going to select VSB or V sigma x? Now remember, what is this equal to? This result here, right? The one in the numerator, this is equal to the variance given in that V vector. Let's call it lambda SB, and this is lambda sigma x, right? Right? Now, which of these two is larger? The denominator, right? Correct. Which means that if I want to maximize this, I'm going to have to select anyone? This one, right? So if I select this one, that is the same as selecting this space defined by this basis vector. And now if I project these three Gaussians here, this first one is going to look something like this, right? This other one and this one, both are going to be identical because they are homoscedastic Gaussians, and they're going to be like this. Now, I can still divide these two classes, this and this, or this and that, as best as ever, right? The empirical error is not going to increase. But for these two, the empirical error, which is something in between here, the base classifier, now has gone from whatever this volume is here to 100%. Right? They're all misclassified. Of one of the classes, they're all misclassified, right? So we have gone from being able to separate these two to being unable to separate the two, right? And the reason is because this one-dimensional vector is not guaranteed to give you the base optimality, right? Only the two-dimensional space C minus 2, in that case 3 minus 1, which would be 2, this two-dimensional space, we are guaranteed, right? Now, if I am here, these are the same, so we'd have selected the exact same one, and I would have this Gaussian distribution here. This one would be projected here, and this one would be projected here. And the empirical error would be the same in that first eigenvector that it is in the original one, right? So in some cases, this algorithm does work, and in some cases it does not, right? To find the base optimal solution. Now you could tell me, well, why don't we just get the two eigenvectors, right, of this metric and find a space where this is base optimal? Well, that may be a possibility in many applications, but in many other applications, it is less than ideal. Imagine that you have 100 classes, or maybe even thousands of classes, maybe even millions of classes, and you want to know what is the one or maybe 2 or 3 variables that are most responsible for something in those classes, right, in that data. For example, you might be studying cancer, and you want to know what behavior people are producing that most relate to specific types of cancer, right? Is it their diet? Is it the amount of exercise? Is it where they live? Is it the amount of money they earn? And so on, right? You don't want to know that there are, say, if you have 1,000 classes, 999 features that explain why people get cancer. That's not going to help us. You want to know what is the one, maybe the 2 reasons, most important reasons why people get cancer, right? There are many applications like this where you do want to know it precisely. That is the point of extracting information from data, right? Of what's now called data analytics or big data, or data analytics and big data. That's exactly what we want to get. So the question is, how can we know? And the answer, so let me show you this here. Let's see if I can turn that on. There we go. So this is the same I was trying to draw. Obviously, this is yet another example. You just have all this in your slides, just nicer, better explained. So if these are the eigenvectors, right, W1 and U1 that we are extracting from our 2 metrics that we have defined, right, W and U, or MW and MU, right, if they both agree, right, if the 2 metrics agree on a solution, then you're guaranteed to get the best solution possible, because both metrics are specifically defined to minimize the base error. And if they both tells you this is the solution, well, then that is the solution. But if they disagree, like in any other case, then in most cases, then you just have to find a compromise, right? And that is defined by the angle between the solution given by MU and the solution given by MW. Okay? And that angle is obviously defined by the cosine of the angle, or you can compute this as the inner product of these 2 vectors. Okay? Now, obviously, you don't have just one vector. You have many basis vectors, eigenvectors for each of the 2 metrics. So you compute the eigenvectors of the first metric and the second metric, right? and you do the inner product of them. That inner product, because these are unit vectors, is the same as the cosine between these angles. And that tells you how much these vectors agree or disagree on a solution. Okay? Now, if they completely agree, then we're safe, right? We know that this algorithm is going to give us a good result. The more they disagree, the less confident we can be on our solution. Okay? So that's a very simple, straightforward way to actually know how confident you can be of that ordering of the eigenvectors. Now again, I want to insist, if you take all the eigenvectors, then you're fine, all the c minus 1. But if not, it's the ordering that matters, right? And that's going to tell you how confident you can be on that ordering, which means that for a specific problem that you might have, there is a solution. You can modify your metrics to make sure that your metrics agree on their solutions, right? And if your metrics are guaranteed to work on your problem, theoretically, then you can be even more confident than that your solution is the one you're looking for, right? So that can provide a mechanism to actually know which metrics to use for MU and MW. Okay? Questions? Yes, please. Then the maximum dimensionality is given by the feature space, right? Yeah. Last lecture, if you go back, you will see in the videos that I said it's the minimum between c minus 1 and p minus 1. Now, obviously, generally, p is going to be larger than c, but it could be in some cases that p is larger, right? C is larger. So, for example, in the last experiments that have been done in face recognition, and when we say face recognition, we typically mean the recognition of identity, right? So I show you the picture of a face, and I want you to tell me who is in that picture. In the last experiments that have been run, I think that they have tested about 1 million identities. So seeds equal to 1 million. So this algorithm is completely useless, because this algorithm will give you the 999,999 dimensional subspace where you can guarantee to be base optimal. Yeah, but it's too large a space to do anything, right? You need, when we get to that in probably a lecture, in our next lecture, when you want to estimate the underlying distribution of a data, right, you probably need of the order of, at the very least, 10 times the number of dimensions, right, to get any meaningful mean and covariance matrix for a normal distribution or any other parameters for any other parametric distribution, right? So think about this. If you need at least 10, and 10 is like the lowest of the lowest you can ever go, right? Ideally, you want maybe 100 as a minimum, I mean. So if you need at least 10, and you have a space of basically 1 million dimensions, then that means that you need 10 million samples. Now, is it possible to get 10 million samples? I mean, everything is possible, right? If you have enough money and time. But it's a hard problem to solve, right? What you would like is to be able to solve the problem with a reasonable amount of resources. Don't cost you to collect tens of millions of samples. Make sense? All right, any other questions? Okay. So all this is a reinforcement of what we have been discussing, which is the non-optimality of LDA and any linear method, as we will see later on. So going back, remember that all we are doing here is solving the classical base classifier equation, where we want to find the argument I from 1 to C, let's say, if we have C classes, that minimizes our discriminant score. This is, remember, called either discriminant function or discriminant score, same thing. And remember that according to the base classifier for any vector t, this is going to be t minus mu I times sigma I inverse, t minus mu I plus the log of sigma I minus 2 the log of PIT. Okay. Now, as we have derived before, in the homoscedastic case, this quadratic component here actually cancels out, and it becomes a linear classifier, and that's why we can solve it. So let me use another notation, maybe. Or actually, let me do this instead. Here's what we're going to do. Let's say that, okay, just want to make sure I use the right notation as in your slides. Okay, right. So what I'm going to do, I'm going to order my means, okay, that I have here according to the basis vector that I select. So let's say that I select this basis vector here, right? If I selected this basis vector, it means this would be my subspace. So this mean would be projected here. This one would be projected here. And this one would be projected here, correct? And I could order them from smallest to largest, right? So I'm going to call this eta 1, eta 2, and eta 3, okay? For the ordered means. Now, it turns out that there is an equation derived by a famous statistician by the name of Geyser that actually derived the base error in the one-dimensional space for homoscedastic distributions. So we can actually compute this, and the error function is given by, for a given vector, right, v, it's given by 2 over c. Let's not call this g because I've used g before for my classifier. Let's call it maybe e, the error function. The sum from 1 to c minus 1 of phi of, let's see, v, negative v transpose mu I plus 1 over 2, where mu I plus 1 is the distance between the consecutive, the consecutive ordered set of means. Okay, so it's a mean vector that connects these two. Now, the reason I can do this is because I'm going to continue here for a second, but let me go back here. The reason I can do this because Geyser's equation, as I said, is given by the sum from 1 to c minus 1 of phi of eta I minus eta I plus 1 over 2. And this phi here, because these are Gaussian distributions, remember, these ones are normal densities. So the PDF of the normal distribution we know, this is actually the CDF, or the cumulative density function, okay? And now remember that in that case, my eta here is this here. My eta I is equal to my mu I that I have, right? Projected onto that subspace defined by this basis vector. And I'm going to normalize this according to the covariance matrix, so I'm in the whitened space, basically, right? Okay. Now, if we use the notation given above, one more step. Here, I am assuming without loss of generality that when I do this, this gives me the order set of means in the vector or in this subspace defined by V, right? If they are not order, meaning that I doesn't correspond to this, then you have to shift this i's, right, for j's. But I'm assuming that they are the same for simplicity of notation. All right, so if we use this, you can show, as we did before, right? We've done this step before, that the LDA algorithm minimizes this, right? Remember that we did this, where we were using mu's instead, right? So we're computing in the whitened space the distance between mu I and mu j. In that case, because we have more classes, I'm doing it from mu I to the average, right? The sample of all my eta i's, right? Sample mean, excuse me, of my eta i's. Right? Okay. So I've added, in the homework, I added a question where you need to prove that this is the same that we've derived before, which should be straightforward. It's like literally 2 lines. Okay. Okay. So this is what I meant when I computed this error function over here, right? This error function is nothing else than using the CDF of the Gaussian that I have from this equation right here, right? But with the means that have been projected, and I'm using the ith mean and the next mean, right? The 2 consecutive means. Now, if I consider a case like this, let's consider this. I'm going to have 3 Gaussians, like in here, right? Like case like this. But now I'm going to whiten my space because I need to whiten it. This is what I did here. So I'm going to have, say, this one here, and this one here. Okay? And let me call these my mu1, mu2, and mu3, okay, for my 3 Gaussians. Now consider that I select this vector, right? That LDA, for some reason, were to select this vector V. Okay, so far so good. Now that defines that subspace, obviously. And then when I project my means, right, this means onto here, I get these values, right? These values here that corresponds to my eta 1, eta 2, and eta 3, right? Yep, that's what we've done. Yep. Okay, now note the important fact now. Let's consider that I move that vector V, right? This vector V is the one that defines my solution space, right? So if that were the solution, that would be it. But what happens if the solution vector is in that direction, right? Maybe it's this other vector right here, right? Then I would be defining another space, one-dimensional space would be this one, right? But if I were to select this other space, let's see, then my projection of the means would still be exactly in the same order. This would still be the first one, this would still be the second one, this would still be the third one. You agree? Yeah? Okay. What about if I were to select this vector right here, right? That defines this horizontal line, the x-axis. What would happen? This would still be the first one, this would still be the second one, this would still be the third one, right? And so on. But if I were to select, say, this one right here, right? Then that would define this subspace here. And whoops, look at this. Now, this one would be the smallest one, so that would become eta 1. This one would be 2. And this one would be 3, right? So in fact, as soon as I go above this line right here, right? So about here, or as soon as I go about this direction, so about here, right? If I go away from this region, right? Then the order changes. You see this? Okay. But this region here, it's a cone, right? Which is nothing else than a convex region. Okay, or region. Now, if that equation that we need to use in here were also convex, this function, then I would have a convex function in a convex region. Then I could use convex optimization algorithms, right? How are we going to prove whether this is convex or not? You know, convex rather than concave, right? If this is for this to be convex, both the Jacobian and the Hessian have to be positive semi-definite, right? They have to only go in one direction. They cannot go in the other negative direction, right? So if you compute the, if I can find this, if you compute both the gradient of our function, the gradient and the Hessian, then the gradient of this function is 1 over c, negative 1 over c, the sum from 1 to c minus 1, 1 over 2 pi, just a normalizing constant, the exponential function of negative c2 square over 2 times mu I plus 1. Okay. Now, to get this result, which you should get it at home to practice these things that we're doing, you are going to need the definition of the CDF of the Gaussian that we have used here. Now, in case you don't have this, I mean, you can Google it. But in case you want to have it here, the CDF of the Gaussian is 2 pi to the power of 1/2, negative 1/2. And e to the power of negative t squared over 2 dt. Okay? And that should go from negative infinity to anyone, because this is a CDF. I sum over from negative infinity to x. Very good. So if you fit in sigma, the CDF of the Gaussian here, and you derive, you're going to get this result. Okay? And from this result, it is obvious that if this is positive or 0, right? As long as this is positive or 0, then this value has to be positive, right? And now let's see whether this is positive or not. In that region, right, that we're considering, because mu I is smaller than mu 2, that's always positive, right? That always goes in this direction. It's always positive, right? But if I'm outside that region, then it may not be positive. It's actually negative at some point, right? So this is positive, definite, if I'm in that region, let's call it, I don't know, A, right? In A. And I'm almost done. I just need to prove also that the same is true for the second derivative. So if I now take the second derivative of E of B, then this is equal to 1 over 4c the square root of 2 pi sum over from 1 to c minus 1 the exponential function of negative c2 squared over 2, and now is v transpose mu I plus 1 times mu I plus 1 times mu I plus 1 transpose, okay? And that obviously is also 0 or positive in A, because this is positive, and this is positive, right? All right, so let's go back to the projector, if I may. Okay, there we go. So this is a better drawing of this, right? This is the order of the means. This is Geyser's equation that we have, that I have shown you. You have all the slides in a link of paper. This is the basic theorem now that basically says that if we have that region, that constrained region A, then this GV is convex, and A, it's a convex region, okay? And that basically means I can use any convex optimization algorithm to find the optimal solution. I have given you here the equations. This shows the different convex regions in which you can optimize. You see these convex regions, or in 3D, right? A little nicer. And now let's see an example of this algorithm in action. So if you use this algorithm instead, right? So you use convex optimization using that function E that we have defined here and find the optimal. Now this is a 3-dimensional feature space with 6 classes. Now you see how they are distributed in 3-dimensional space? See that, everyone over there? Yeah? Now, it seems weird that there is actually a 1-dimensional space that can separate all these 6 classes, but there is. They say in 3D there is one vector right here that gives you this result, okay? And this is what this algorithm finds, because this algorithm is guaranteed to give you the base optimal solution, right? I mean, we just proved that I can find it. This is what LDA will give you. It's just a disaster, right? Because it's basically almost at random, almost at chance, because every Gaussian in the 1-dimensional space represents 2 classes now, right? So I cannot distinguish here. I cannot distinguish between class 1 and 2, class 3 and 4, and 5 and 6, right? That's terrible. But there is an algorithm that allows me to find this, right? That's pretty cool. Okay, so, one more. So that allows you to find the base optimal solution, meaning the one-dimensional feature space, okay, or subspace, where the base optimal is minimum, right? There's no other one-dimensional subspace in my feature space that's going to lead me to a smaller empirical error or expected error. No way. It just doesn't exist, right? I know for a fact. Now, that's under the assumption still of homoscedastic Gaussians, right? But there is no way. We'll get to the point later on in the course on how to solve these issues of homoscedasticity assumptions. But what happens if I want to find the two-dimensional subspace, right? Now I want to find another dimension. That algorithm doesn't work for that. It's not going to give you 2 dimensions. It only has one v, remember? So it's only going to give you that one basis vector. But what you can do is, once you have found your solution, v1 here, right, this v1, you can project everything onto the null space of v1, and then reapply the algorithm on that null space, right? And you can keep iterating this ad nausea until you're tired of getting dimensions, right? So for this particular case here, this would be the first base optimal solution. This would be the two-dimensional optimal solution. All right. So let's review this very quickly. I posted the paper PCA versus LDA. I recommend you read this as to just review all the notations or all the derivations that we have given in class. Remember, PCA, this is fundamental to understand everything that we've done thus far. PCA maximizes correlations, right? The goal of PCA is to find the vector V for which the correlation between my samples is maximized, right? Okay. We can also then model, as we have seen, that set of points as a distribution. If I were to use a normal distribution, then I estimate the mean and the covariance matrix. If I use a sub-Gaussian or super-Gaussian, then I estimate the parameters of that distribution that correspond to it, right? Now, if I know the distributions, I could compute the base classifier given by this equation here, right? And we've shown this is the smallest error I can ever have. Super important to remember the base criterion, because that is going to be fundamental for us for the rest of the course. This is a summary of the metrics that we have been using and what I've said. This is, I give you here an example or a couple of example applications maybe in the slides. This is to align fMRI data. That fMRI stands for functional magnetic resonance imaging. So MRI, it's a classical image that you're going to take in this big donut shape machine that you may have been into if you've ever injured your knee or something, right? Or a tendon. They'll put you in this machine that's very noisy, makes a lot of weird noises, right? So you probably have to wear earplugs or something to avoid damaging your ears. And you cannot bring any metals into it, right? Because this big donut, what it actually does, it creates a very stable magnetic field, okay? And then there are radio frequencies that are sent that disturb that field. And then depending on which type of tissue this radio frequency goes through, it has a bouncing back time into a stability of the magnetic field, longer or shorter. And by computing how long it takes for the magnetic field to recover in the specific areas, you know what type of tissue you're looking at, okay? Now, functional MRI goes a step further, and what it measures the amount of oxygen in blood, Okay, so it's actually measuring how much oxygen there is in a specific area of your blood vessels, right? And that allows us to measure the computations that the human brain is performing at a specific period in time. So we're actually looking at the activity of the brain in vivo in humans and animals, right? That is because when neurons are firing or processing computing data, they use oxygen. So they require more oxygen to be sent to that region of the brain. Okay, so there is a correlation there that we are taking advantage of. Now, the problem is the following, both in MRI and fMRI, but especially in fMRI. Okay, so let me give you, so this is probably a little blurry, but this would be an MRI image that you could get of a brain. This would be the corresponding fMRI image, and you see this, these green areas right here and yellow and red areas right here. Those correspond to the activation, meaning the amount of oxygen that there is in a specific area of the brain at a specific time. Okay. Now the problem is the following: when I take a picture of your brain and someone else's brain and my brain, they're different, right? Not all brains are exactly the same shape. They're close, but it's like a face or a hand, right? They're pretty similar, but they're not the same. So if you want to use machine learning algorithms to do analysis on this, you have to do what? Remember what the first step I said that you have to do is? You have to align the data, right? Correct. Remember that with faces, we said the eyes have to be in the same location, the mouth in the same otherwise, you're comparing eyes with mouths. It just makes no sense. Well, the same applies to the brain. You have to align the brain. So what people had been doing for many, many years is they were aligning the brain to a simple mean brain, right? So that simple mean, usually called the MNI. MNI is one of them. The MNI brain is a simple mean brain that people compute from, I forget, with 60 or 40 plus subjects, right? So they put them in the scanner, they took their MRIs, and then they compute the mean shape of that brain, the mean three-dimensional volume. And now once you have a new brain of a new individual, you register that new brain into that standard simple mean, right? But when you're doing that, first, this is computationally expensive. But second, and most importantly, you're losing data in two potential ways. One is maybe you have to expand the brain in certain areas because the standard brain or the simple mean brain is larger in a specific area of the brain of your subject. So you have to create or use interpolation to guess what would be in that region that doesn't exist. Or, even worse, the area in the simple mean brain is smaller than in your subject's brain, and you have to reduce the resolution of that area, meaning you have to eliminate data that you do have. Right? Terrible. Why you ever want to do that? But those are the limitations. There's another solution, which is to use both PCA and LDA, right? Well, just basically PCA for now. And the solution is that here in the brain of the subjects, so these are two brains of two real subjects. This is actual real data that we have collected here in our fMRI, in our MRI machine here at Ohio State. So as you can see, the shapes of these two brains are slightly different. And that means that the number of voxels, now what's a voxel? A voxel is a three-dimensional pixel, right? So when I take a picture of your brain with that big machine here, it's a few $1 million machine, right? Things like $10 million machine. It's an expensive camera. There's nothing else on the camera. It takes a picture of your brain, but instead of taking pixels, it takes voxels, right? Pixels are two-dimensional, voxels are three-dimensional, okay? So the number of voxels that I have in that brain are different, right? That's why I need to align them. But I can align them functionally instead of anatomically, because remember, I'm interested in this activation here. I'm not interested in the anatomy. I'm interested in the activation. So what I can do is, you see, for this subject, voxel 1, voxel 2, and so on, right, up to many dimensions, the activations that I observe in each of these voxels when the subject is performing task 1 versus when it's performing task 2 look like this. And in this other subject, they look like this. Right? It's slightly different. Why? Because voxel 1 in subject 1 represents something else or something different than voxel 1 in subject 2. But because I know that they're both performing these same 2 tasks, I can now align this with this. How? With PCA. That's what PCA does. It's a linear least squares alignment of this data, right? So if you compute the covariance matrix of this and the covariance matrix of this and the eigenvectors of that covariance matrix and that one, and then you align the principal components, right, the eigenvectors, then you can project the data in a common space, and then it looks like this, right? So the data has been aligned. And then you can just use a classifier, base classifier, if you estimate the underlying distributions to be, say, normal distributions, or you can compute the LDA dimension if you want to, okay? All right, any questions before we move on? No? All right. Before we close this section and we move on to our next super important topic, which is mixture models. So what we're going to do until now, we have been assuming that our classes are given by a distribution, right? But that is obviously very unrealistic. I mean, what are the chances that my data is going to be defined by a Gaussian distribution, or even a super Gaussian or a sub Gaussian, right? They're tremendously small. So we're going to talk about something that's called mixture models, where you can have multiple distributions defining your classes, your data. Okay. But before we do that, let me conclude this with a few pointers to you in case you want to dig deeper into this area, because this is a fundamental area that has so many applications, especially these days in big data and data analytics. So first of all, obviously, I've talked about convex optimization here. You know about this. You've hopefully taken optimization. If not, if you want to know more about this, we have courses here on convex optimization and non-convex optimization that I keep alluding to, but that you should consider because most of machine learning involves some type of optimization. Now, you can, and most people do work in machine learning without being experts in optimization, because you're going to have a colleague of yours here at the university or at the company that you're going to work in that is an expert in that, right? Fair enough, but at least you should be familiar with the fundamentals so that you can talk to that expert, right? So let me give you some quick review of some basic formulations. So we are going to use this constantly, so it's important to know. So remember that an optimization problem takes the following form. I want to either maximize or minimize, let's say minimize, some function, say f0 of x, subject to, and then we're just going to usually just write s dot t dot, right? S point, t point, meaning subject to some constraint, and that constraint, let's say it's going to be another function. Let's call them fi's, right? One or many functions of x, smaller equal than the bi's for I equal, I don't know, 1 through n, okay? So you have multiple, you can have as many constraints as you want, right? So you have a function that you want to minimize or maximize, and subject, the maximization, minimization has to be subject to some constraints. Okay, now this top function right here, now tattoo this in your brain because this is the formulation that we're going to, or the notation that we're going to use throughout the course. This is obviously called the objective function. And you will see whenever you read any book, any paper in machine learning, you're going to read, you're going to see our objective function is this, and we derive this objective function like this because what have you, right? This, and that. And we are going to be doing that. The objective function is the most important thing. And then subject to, and these are my constraints of functions and the constraints for these functions, the BIs, the actual constraints for these functions here. So for example, let me give you maybe some examples. For example, what would this do? Let's say I want to minimize f of 0, which is capital X, where capital X, it's a matrix with all my samples in it, right? Times a vector A minus some D, 2 norm squared. No constraints. We have actually seen this. What's this called? Anyone? Very good. Linear least squares, right? This is linear least squares. That's just the way you write it, usually, right? Now, in general, when, let's see, when the objective function, the objective function and all your constraints here, all your functions that define the constraints, they're all linear functions, then this is called a linear program. Okay? All right. And when they're not, it's called a nonlinear program. Very nice. When the objective function and the constraints satisfy this following equation, let's see, x1, x2. When you use alpha x1, beta x2 is smaller or equal than alpha times f1 x1 plus beta f2 x2. This is called, anyone? Very good. Convex optimization problem. Okay? So convex is more general than a linear problem. Okay? Of course, linear least squares is a convex optimization problem, right? That's why we could solve it, right? Because it's convex. Anything that's convex can be solved in relatively easily with convex optimization algorithms, right? Anything that is non-convex cannot be solved easily. We have introduced nonlinear least squares, and we'll get back to this type of algorithms shortly to define mechanisms to find solutions for non-convex problems. So here's an example of a convex optimization problem that we have seen when we have defined the base classifier. It's given by minimizing the W times X subject to the following constraint, W or some AIs, say it's just some AIs times X, smaller or equal than BIs, right? For I, again, 1 through N, or let's say M, because I've used N for, let's change this to M, just to not confuse it with the number of samples. Okay? So we've seen that before, right? Okay. How about, this is for our objective function and constraints. How about a convex set? Now, if I want to define a convex set, actually, let's talk about maybe an affine set first. So, we'll say that a set S, let's say that this set is affine in our feature space, a real domain of p dimensions, okay? Is said to be an affine set if the line that passes through any two elements in S is also in the set S, okay? So we can rewrite it if you prefer. Let x1 through xk or xn, to be consistent with our notation, be defined in Rp, right? And let's define our coefficients alpha i's to such that they add up to 1 from 1 to n. And then I can write that the sum of alpha I times xi has to be in S, okay? Make sense? Okay. Now, a convex set means that any two elements in that set have to, what we usually call, see each other, right? Such that if I am, say, here in this ellipse, right? If I have these two elements, there is a line connecting these two that is within that set, right? That there is a direct line. Compared to a non-convex, where these 2 points do not see each other because they cannot cross the empty space outside the set. So in the derivations of the base optimal solution to the LDA algorithm that we have provided here, we had the particular case of a set called a cone. Remember that area A, it's probably still here, this area A, which is defined as a cone, that's a particular type of a convex set, right? So you could define a cone. So let's do that as an example. I could define a cone as alpha x, right? With C, or alpha I, xi, with all the alphas larger than 0, right? And then I get this shape that we call a cone, right? Note that the hyperplane, right? The hyperplane that we have been defining as our classifier in the base classifier, the hyperplane is an affine set, right? Correct? But the half space, the hyperplane defines two half spaces, right? Of one class and the other class. Half space is not an affine set, right? It's a convex set, but it's not an affine because there's a line that crosses from one half space to another, right? So it's not necessarily the same. You can write the two half spaces that you obtain when you use the base classifier to the linear base classifier in the homoscedastic case to obtain the base optimal solution. You could define them as x in W transpose X that is smaller equal than B. Now remember, B just tells me where that half space is, right? And W, the norm, so the orientation of that half space. And the other half space would be given, anyone? What's that? Okay, larger or equal than B. Right? So these are my two half spaces. And that's how you usually see this written. All right, so these are not, these are convex sets, obviously. Another convex set that we have seen is the p-dimensional ball. Now remember the p-dimensional ball, right? It's the ball such that every element in that ball constitutes the actual solid object of a ball. But the sphere, SP, that we have used also, that's only defined by the points on the surface of the p-dimensional ball, right? That is a non-convex set, right? Because I cannot go from every point to every point in a straight line. There's a non-convex set. That's what makes the sphere such problematic to derive algorithms. We have also seen another type of set that is very useful, which is given by all the x's that satisfies this equation that you should be very familiar with by now, hopefully. Right? And that defines an ellipsoid, right? It's a type of metric that we have been using. And all those are also convex. Okay. Let's see, what else can we review quickly? All right, I think I'll leave it at that. So maybe one final one. So it is important to note that there are many functions that preserve convexity of a set. So for example, the intersection, an affine, or a perspective function are all going to preserve the convexity of a set. That's important to remember. Intersection, remember, means that if we have two sets, S1 and S2, that are convex, then I have S1 intersection with S2, right? So the common part of the set. And in general, remember, if you haven't taken image processing, you should remember that if I have a function from P to Q dimensions, and that function is given by a matrix, a non-singular matrix X, A, and a vector B, that is called, anyone? An affine transformation. Very good. All right, leave it at that, and we'll start the next topic in our next lecture, which is mixture models.